Hello everyone, welcome to Women in Ethereum Protocol Cohort 4 study group. And today we have Marius with us. He's from the Geth team and he will do a deep dive today about the execution layer of Ethereum and Geth. So over to you, Marius.
Thank you. Hey all, it's nice to meet you all. Yeah, I'm Marius. I've been with the Ethereum Foundation for 5 years now. And before that, I did also work in crypto. I did some like payment and state channel stuff, which was like scalability technology. But in 2020, I joined the Geth team and I've been doing core development ever since. And now my neighbor started to cut some trees down. I hope you guys can still hear me. All right. And I'm just going to start. So I didn't have that much time to prepare because I've been very busy in the last couple of weeks. So this is going to be not super structured, but I hope that everyone will like take away a bit about execution layer architecture, and I will try to link some resources and also in the end get the slides and everything to you so you can study it yourself if you want to. Okay, let me share my screen. I have a bit of a presentation, but it's only like a few slides, and I'm probably going to switch off of them at some point to show you some stuff in the code so that we can like actually go through the code and see how this actually all works. So bit of a small background. Go Ethereum is one of the 5 implementations of the Ethereum protocol. On the execution layer, our responsibilities are to verify and distribute transactions. This is called the transaction pool, and we create and verify blocks, and we provide access to the state of smart contracts, and we also provide some debug functionality. There's roughly 7,000 Geth nodes on the Ethereum network right now. I think it's actually much more than that at this point, but I stole this from a very old presentation. Basically, you can think of the Ethereum network as like, I don't know, like a bunch of people that are connected to each other. And if you send a transaction, like if I don't know, if this alien wants to send a transaction to this person, what it does is it will create the transaction and then it will send it to its local node, either via like creating the local node and running the local node, or via Infura or some RPC provider that runs a node for them. And this node will broadcast the transaction to everyone. And then the next miner will take the transaction, put it in a block, and mine a block with it. And so basically, as you can see, these slides are a bit old now because it still has the distinction between pre-merge and post-merge. But basically, before the merge, like you can very easily download and install Geth from the website, and when you start it, it will start downloading the blockchain, and it needs roughly, this is also very outdated, it needs roughly like 1 terabyte of space. And yeah, so this is where we are kind of right now. During the merge, like previously before the merge, the execution layer client would do everything. They would create and verify the blocks. They would pick or choose via proof of work, choose which node can produce the block, and so on. And after the merge, we split this functionality in 2 parts. I think I've seen that you guys already had someone from the consensus layer client teams on to talk about like their part. But the idea is behind the merge is that basically the execution layer is very good at a certain subset of things. It's very good at providing access to the state. It's very good at executing the transactions, verifying that the transactions are correct. And the functionality that has been factored out into the consensus layer client is basically choosing which blocks to execute. So we kind of have in practice 2 chains. We have the beacon chain and we have the execution chain, which is kind of built into the beacon chain. And what happens is this consensus layer client tells us, hey, this is a new block. Please verify that this block is correct. And we need to make sure that the block is correct, that we have the state for it, and so on. And let me switch over to my code. I hope it's big enough so everyone can see it. But we can kind of start by seeing where the consensus layer node tells us, hey, this is a block that you need to execute. And for that, we provide the engine API. If you go back to this, basically the engine API is the glue between the consensus layer and the execution layer. And the engine API has a bunch of methods, like the methods can be found. We refactored that part. But basically there are four big methods. It's new payload, get payload, fork choice updated, and then get blobs. And the first one, and arguably one of the most important ones, is new payload. New payload, basically with new payload, the consensus layer tells the execution layer, hey, this is a new block, please execute it and try to execute it and tell me, is it valid or is it invalid? And so what we do is we call new payload, and first of all, we get the data as JSON, like all of the interaction between the execution layer and the consensus layer is in JSON. So we get the JSON payload, and we need to turn it into our internal representation of a block. It's we kind of do that here, and we verify a bunch of things, like preconditions that the block is kind of correctly looking. So for example, if like we have an extra data field, which can be used to put any data into the block, but we limit it to 32 bytes. So if someone puts more than 32 bytes into a block of like this extra data field, then we say this block is invalid. Or this logs bloom field has to be 256 bytes in size. Okay, so now we have our internal representation, and if we encounter an error, we return like this block was invalid. Now, if we already have this block and we already know, okay, this block is a valid block, then we just return, hey, this block is valid. But now we also need to, if we don't have this block, we need to insert this block. And inserting the block means we have to execute the block. And executing the block, like first of all, we verify a bunch of stuff, so that the headers of the like the header of the block is correct and so on. And then we kind of do the whole EVM execution. So this is where we execute the transactions and the kind of like every interaction of the users. And we can find this here, process block. And within process block, we process go to the state processor. This is conditions. And the important part is basically here, apply transactions, apply message. So here we are in core state transition. This is basically where all of the magic happens. And so this is the actual EVM implementation. And what we do here is we start the. So this is for every transaction, we execute what this transaction is actually doing. And that starts by checking, does the sender have enough funds to send this transaction? Does the sender have enough funds to pay for the gas in this transaction? If the gas exceeds the limit of the block, we will return an error and so on. So this is what we do in pre-check, and then we compute the intrinsic gas. Like this is not really important. The important thing is, oh, I missed it. I missed the important part. The important thing is here. Basically, we either, if we have a create transaction, if we have a transaction that creates a new smart contract, we will start the EVM with a create function. And if we call into an existing contract, we will start the EVM with a call function. Let's say, okay, our first transaction in our block creates a smart contract. And we can maybe quickly like show our transaction types, legacy, for example. So this is a transaction type. So this is what's in the transaction. You have a nonce. So basically, this is an increasing number per account. If you send a transaction, you know, okay, like you have sent 13 transactions. So the next transaction that you send has to have number 14. Otherwise, if you send transaction 15, the chain will reject it because it hasn't seen transaction 14 yet from you. So this can be used to kind of order the transactions that are coming from your account. So if you want to send 2 transactions and you want to have them in a specific order, you will order them by nonce. We have the gas price. This is how much you are willing to pay for your transaction for each unit of gas. So all of the operations that we are doing in the smart contracts are denominated in gas. So for example, if in your smart contract, if you add 2 numbers together, then that costs you 3 gas. And if you multiply 2 numbers together, that costs you 5 gas. And what you need to specify is how much money you are willing to pay per individual unit of gas. And this is basically how you specify how much you want to pay for the transaction. And then you have to put a limit. Otherwise, we don't know whether you want this transaction to run forever or not. And so you have to put a limit what you're willing to pay for in gas. You have the to field, which means I sent this transaction to that contract, or I sent this transaction to this person, and then you can attach a value to it. So you can say I sent 5 euros or 5 ETH to this person, or I sent 5 ETH to this contract. And then you can put some data. And this data, if you send your transaction to the 0 address or the nil address, then it means you create a contract with this data. If you are sending this transaction to a specific contract, then it means you are invoking the contract with this data. And then the contract will start executing its code based on the data that you give it. And then you sign the transactions. And like from recovering the signature, we get your public key, and with this we also get your address. And so we can look back here and see, okay, if you want to create a contract, you will jump in here, and it will use the data field that you put in, and then it will invoke the create operation within the EVM. But I think this is going a bit too far today to look into how the actual EVM implementation works. But what you can see, like we have kind of all of the EVM implementation is bundled in the core/VM package, and all of like the outer handling of the transactions is just in the core package. And so we're always trying to provide different modules for different things, so that people can say, okay, like maybe for an L2, instead of just executing all of the transactions, they want to also introduce a new transaction type or a new transaction that is always run at the beginning of the block. And so they would still take the same EVM, but they would kind of modify the outer layer of the EVM. And yeah, so now we can kind of go all the way back. Basically, we applied our single transactions. In this loop, we go through all of the transactions in the block. And at the end, we say, hey, this block was valid, or we return an error. And so we go back to the API. And basically now we tell the consensus layer, hey, either this block is invalid or this block is valid. Or the third thing that can happen is we don't know yet. And when is the case when we don't know? That can only be the case if we cannot execute the transactions yet. And this happens if we don't have the state. So basically, when you start up your node, you don't have anything, right? And then someone tells you, hey, please verify, like you are at block 0. And then someone tells you, please verify block 20 million. And then you say, hey, I cannot verify block 20 million because I have not verified the block 1 or 2 or 3 up to like 19. So I cannot actually verify block 20 million. And so what we need to do in this, when someone tells us, hey, please verify this block, and we don't have the previous block, then we need to go to the network and say, hey, I'm not synchronized with the network. I need all of the old blocks, and then I get all of the old blocks from everyone, and then I can execute them and verify them and kind of make sure that I have the actual state. So I think this is also, yes, this is also what I have here on the slides. So basically we have different synchronization modes. And for full nodes, we have 3 different synchronization modes. We have the full sync, where it downloads all of the blocks and executes all of the transactions. But this takes a long time. This takes roughly 3 weeks. And then we have the archive sync, also downloads all of the blocks. It also executes all of them. But we, in addition to every to the latest state, we also store every intermediate state. So basically, I didn't really explain the state very well. So I'm going to do that now. Basically, what Ethereum kind of is, or the EVM kind of is a state transition function, right? Like you have a state X, and then you have a transaction, TX1, and then you have a state X prime. So this is basically what a transaction does. You go from a state to the next state. So for example, the first state would be like A has 3 and B has 5 coins. And now so like this is X, and now our transaction TX1 is A sends to B 2 coins. And now the new state, after we applied this transaction, X prime would be A has now 1 coin because they send 2 coins to B, and B has now 7 coins. So this is what I mean with the state. The state is all of the balances, all of the smart contracts, all of the storage that is in the smart contracts, all of the contract code, and so on. And the transactions are kind of the differences between 2 states. And what we do in a full node is, in this scenario, we would just forget X. We would just store X prime. Like we would do this computation once, and then we would forget X. And in an archive node, we would still remember X. And the difference between remembering and removing it is, I think, roughly 30 terabytes. So if we remember every single, like you can, like all of the, like now TX2, and it will result in X prime prime, right? So if we store all of these intermediate states, that's roughly 30 terabytes of storage that we would need to store. And for most people, it's not really important what happened in the past. The important thing is like, what's happening right now? What is my current balance? How much money do I have on my account? How much money can I spend? What is the smart contract that I want to interact with doing right now? And it's not really interesting for you. What has it done like 5 years ago? And so that is why most of the people don't run an archive node, but they run a full node. What we can also, like basically in the full sync, we download X and TX1, TX, and so on. And then we compute, well, not and so on, it's only 2 transactions. And then we compute X prime prime, and we store only X prime prime. In the archive sync, we download X, we download TX1, we download TX2, we compute X prime prime, and we store X, X prime, and X prime prime. Now, this like executing every transactions, we have I think we have almost 3 billion transactions at this point. So executing every transaction takes a really, really long time. So what people came up with is the snap sync, where we just download X prime prime, and we only store X prime prime. And so we don't need to we technically do download all of the transactions, but we don't execute them. And we wouldn't really need to download all of the transactions. So this roughly takes 7 hours. and these take like 3 weeks each. So there's a big difference in the speed that we do. And then we have this is also outdated. Don't look at the pruning stuff. And then we have light nodes, and these only download the headers. So basically, what we have in Ethereum is basically we have a block, and each block has a header and a body. And the header contains like the hash of the parent. So this is kind of the blockchain, right? Like the header contains the hash of the parent and the hash of the parent and so on. And it contains a bunch of hashes and a bunch of things. For example, a number and the gas limit and the timestamp and so on. And it contains a body. And the body consists of the uncle headers, which we don't use anymore after the merge. And most important, it contains all of the transactions. So what we do in the light sync is we only sync the header chain, which is roughly 20 gigabytes. No, I think it's 15 gigabytes. And we don't download all of the transactions. And downloading all of the transactions is roughly 400 gigabytes or 300 gigabytes, and then there's like another 300 or 400 gigabytes of receipts. Yes, but I think that would be a bit too far if we go into this. Okay, so what have we learned? The Ethereum execution layer nodes have very broad areas of concerns. We have the EVM which executes the operations. We have the engine API, which is the connection between the EL and the CL. We have something called the miner, which is responsible for creating blocks. And like if you want to find that in the Geth database, you need to go to core. No, where is it? I don't remember. No, I think it's in miner. Yes, here is, and this generates the blocks. So that is the other thing that you can like. Oh yeah, I kind of stopped here. Yeah. So basically, one thing that the CL can tell you is, hey, please execute this block. But another thing that the CL can tell you is, hey, we are chosen to produce the next block. So please, based on this head, please produce the next block. Based on this parent, please produce the next block. And this is what fork choice updated is for. Fork choice updated. And fork choice updated has multiple kind of meanings that are interwoven. And I think that's also a thing. Like I'm not very smart. I'm very stupid. And I only know this stuff so well because I've been working on it for a really long time. But when I joined, I didn't really know any of this, and it was a really, really hard work to get here. So if you are seeing this and you feel kind of a bit overwhelmed and you cannot really follow, then I think that's partly because it's a bit late here and kind of I'm kind of rambling on. But on the other hand, it's also, this stuff is just it's not as complicated as it seems on the first time that you hear about all of these things. So I really want to encourage you to don't be discouraged if you cannot really follow what I'm saying or what the people have been saying in these calls, because they've been working on this for a really long time, and sometimes it's hard for us to kind of break it down onto a level that is easy to understand for everyone. So yeah, that's all I wanted to say is don't be discouraged by if you don't really understand everything that I'm saying today. And I want to encourage everyone to sit down and look at this and try to find their niche where they can contribute. Because I don't know, if I would hear this similar talk given for the consensus layer, I would also not be able to follow very much, because people are very they kind of find their niche in the protocol, whether it is, I don't know, like the gas schedule or like the EVM, or it is the consensus layer or the execution layer or the networking. And most of the people have a very good understanding of one piece of the code, and then a very broad understanding of everything else. Sorry for this tangent. But basically what this fork choice updated does is it basically tells the node, hey, the block that I just gave you that you should tell me whether it was valid or it was invalid, this block is now considered, and you told me it's valid, then this block is now considered the new head. And head is always the newest block that we have. If we have, the problem is if we have like, if we have a fork, so we have this block and this block is the parent block, and then you have two blocks building on top of this. So we have like this block is A, and then we have this block is B, and then we have this block is C. And both B and C have a parent of A. Now the question is, like, how do we choose whether the next block is whether this block is the next block or this block is the next block? Fortunately, that is happening on the consensus layer, so I don't really know, and I don't need to know. But what the consensus layer needs to tell us, first of all, so in this case, it would first tell us, please execute B and say if valid. And then it would tell us, please execute C and say if it's valid. And then it would say, because then it knows, okay, this block, for example, this block was valid, B was valid, C was invalid. And then it can say, okay, then I'm going to vote for B. And then afterwards it will tell us, okay, please build a block on top of B. And then we are asked to build a block D here. And so this is how we like continue on the blockchain. And this again happens here in fork choice updated. Basically, it will tell us like pick this block, and then it will tell us, hey, on top of this block, please build a new block. And now the problem is that this block building takes time, roughly 200 milliseconds. And so we don't want the consensus layer to be waiting for 200 milliseconds until the block is done. And so what we tell the consensus layer, hey, we are creating a block, and this block will have this ID. And then later on, the consensus layer can call get payload with the ID, and we will either tell it, hey, we haven't finished building yet, or it will give the block to the consensus layer so the consensus layer can propose it. Yeah, so this is kind of like the mining part. These databases, they are not really important. Basically, we store the historical blocks, and we also store some historical state, but we have like, this is kind of back to this picture here. So for example, here x and x prime would be the historical state, and x prime would be the new state. So we would store the historical state in the ancient database, and we would store the new state in the state DB. This is a bit of a weird concept, but we have to store the state in two different kind of versions. One version is for being very fast with executing, and one version is for creating the state root at the end of the block. But I think that would go a bit too far if I would go into the TryDB now. Other important areas that you should have heard of when talking about execution layer architecture, the networking. So all of the Geth nodes, or like all of the execution layer nodes, are connected to everyone else, or not everyone else, but like to a bunch of nodes, in order to send transactions between each other and for this initial sync. So when you start up the node, you need to ask for all of the blocks, and they will be provided by your peers. And also, like if you send a transactions, you want to send it to all of your peers, so they like the transaction gets distributed in the network, and the chance for you to get included into the next block is kind of high. So this is kind of what the transaction pool is about. The transaction pool maintains these in-flight transactions. So when the miner creates a new block, it will ask the transaction pool, hey, I am tasked to create a new block. I need all of the transactions that are available. And the transaction pool maintains like a list of the transactions that are available that have not been included in a block yet, and that where the sender has enough money to pay for the transaction. And again, the networking through the network, we get the transactions, we take these transactions, we put it in the transaction pool, and then out of the transaction pool, the miner can pick the transactions and create blocks with it. The transaction pool itself is actually quite a complex piece of software, because there are a lot of transactions, a lot of attacks that you can make for the transaction pool. So, for example, what you could do is like one scenario would be like I send 100,000 transactions every second to my peers, and then my peers would like quickly get overwhelmed and wouldn't be able to function anymore, because they get just overwhelmed by the amount of transactions that they receive. So the transaction pool has like a lot of limiting built in, so that, for example, per account you can only store, I think, 16 transactions or so. Or like that someone, like if someone would send a transaction that is not really executable, but it pays a lot of money for the transaction, then it might become useful in the future, right? Because it pays a lot, but it is, for example, it's non-scapped, or the sender doesn't have enough money to pay for it. So the question is, do we store it or do we throw it away? What we can do is we always throw it away, but then it also has an impact on user experience, because if you send a transaction that like if you send TX1 and TX2 to the node A, and then at node A we receive TX2 and then TX1. If we would always throw away the transaction that is not executable, we would throw away TX2. But if we just waited a tiny bit, then we would get TX1, and then we could have TX1 and TX2 in our transaction pool. And so the transaction pool is full of these like very complicated, very weird rules. And there's also has been a lot of work done on like trying to model the transaction pool, trying to figure out attacks against the transaction pool, trying to fuzz the transaction pool. And then, as I already said, the downloader, when you initially join the network, you need all of the blocks. So you ask your peers for it. And this is also a very, very complex piece. Again, because you don't want to, like, if you're connected to a malicious peer, then you don't want them to give you blocks that are invalid, because you need to have like a way of verifying that these blocks are correct. And then another big area of concern is the RPC. Basically, I don't know if you have been using MetaMask or like a wallet already, but when you use a wallet internally, it sends requests to either an RPC provider or a local RPC node. And these RPC providers, they basically just run like standard nodes and expose this RPC. And so the RPC contains methods like ETH. We can quickly just can I find terminal? We can quickly run a node. Go Geth dev console gives you a development node, which is kind of nice, because we can use it to do development stuff. We don't need to set up a consensus layer. Like there's like a small consensus thing built in, simulator built in, so that we can do some stuff. These are basically all of the things, the RPC that we provide. So for example, ETH get block latest will give you the latest block. And you can see, okay, the latest block is block number 0. And now we can create a transaction. There's always kind of a private key built in. I don't know if I can send transaction. I don't know if I can do this on top of my head. It's something like from this itself. I cannot paste in this terminal, which is really weird. Something like this. No. ETH send transaction. Yeah, this has to be the function call. Yeah. Aha. And now so what we did is we submitted a transaction with this hash from this person to this person, which is itself. And then, as I said, there's in this dev mode, there's like a little consensus client built in that just creates a block. And so what we see, we start work on a payload, and then we have a payload that has one transaction, and then we stop the work on the payload, and then we import a new potential segment, and then we update the head. What we can do now is we can see if we do again ETH get block latest, the latest block is number 1, and we can also see, okay, this block has this transaction in it with this hash, and if we go back and see what the transaction hash was, this was the transaction hash. And you can see this is basically what you see here is the header. And if we do true, then we see the header and the body. So this shows you the header, and this here is the body. And you can see the transaction that we send. It's from this person to this person. This is the hash of it. This is how much gas it used. This is how much we were willing to pay per gas, and it had non-zero. So if we send another transaction and we do the same thing, and then we see, okay, this is a transaction again from this person to this to itself, and it has a different hash, and it also has a different nonce. So it's basically increasing in nonces. Yes, I think we have another 10 minutes. I would just stop at this point and we do a bit of Q&A. If you have any questions, either about this, about core development in general, about anything, yeah, let me know. I'm here for the next 10 minutes.
Hi, Marius.
Hey.
My name is Judith, and I am just curious. Your code base is strictly on Go. I've not interacted with Go at all. I don't understand it. So I'm feeling so disappointed with myself that I won't be trying any good fast issues. I don't know, what advice would you give? Because you explained it so well that I feel like, oh, this is good. I was liking the concept because previously we had Matthew explained the consensus and it was amazing. So I was curious, how did these two connect? So now you've explained and I'm putting it all together and I'm thinking, wow, as you said, it takes a while to understand, but at least I'm getting the baby steps to understand this. So usually it makes more sense when you start contributing and then asking questions and then reading more about what you're doing. But here I don't even do Go. What would you advise? This is so cute though.
So the cool thing is, yes, our code base is in Go, is written in Go, but there are other code bases written in other languages. We have Nethermind written in .NET, C#. We have Reth written in Rust. There is Ethereum JS written in JavaScript, and there is the specs. The specs is written in Python, and the idea behind the specs is similar to the consensus layer specs. I think Justin was already on and maybe talked a bit about that. Basically, you create a specification that is on one hand just a specification, but on the other hand, it is written in Python, so it can also be used to create tests and so on. So if you are proficient in any, basically there's a client in almost every programming language, even JavaScript. So if you are proficient in any language, any programming language, there is something for you. I think the easiest way would just to look for, I don't know, Ethereum client language, and you will find something.
I have a question. So I think the execution client stores the state data, right? If I'm not wrong, which which data structure is used, like, and which part of the code is it where the data of the entire state data is stored? The try
That,
DB and the state DB. Yeah.
yes, I kind of glossed over that. I can go a bit deeper into it. Basically, we are storing it in two different data structures. Let me quickly share my screen again. If you look at the Ethereum try structure, then you will come across, God damn it, he deleted this image. You will come across this image. The open image in new tab. This image, which tells you nothing. It's super stupid, but this is like the best visualization that we have of the try. Basically, we store the try in, like, we store the state in kind of a tree structure, but instead of, I think if you took like programming 101, you kind of know what a tree is, but you usually think about it in like binary tries, where you have like one node and this node has like two children. Like every node has like two children. Let me find a try tree, like something like this. So this is kind of what you this is kind of what you think about when you think about a tree. We use tree and try interchangeably. There's a slight difference, but we don't really know the difference. Basically, this is what you think about if you think about a tree. But what we have is we kind of have a hexary tree. So every node has 16 children, 0 to F. And every child can have, and every child can either be an account, which is called a leaf node, or it can be an extension node and then another branch node. So basically, like if we remove the extension nodes, because the extension nodes are like an improvement that you don't really need. Basically, the idea is all of the I cannot really draw that, but basically every branch node, every node has 16 children, and one of those children has another node, and so on. And at the end, you arrive at an account, and this account again has the storage tree, and this is the same structure is basically in the tree. I can quickly draw it here. I don't know if you can see this. So basically what we have here, we have one node. So we have is this visual?
Yes, we can see it. Yeah.
This one. So we have one node. This node has 16 children, and each of those has 16 children again. And at the end, you have an account. This account says, okay, like there's 3 ETH in this account. And so the question is, like, who does this account belong to? Now we know, okay, this is this is 0, this is 1, this is 2, and so on. And we can see, okay, like this account belongs to, like, the first letter is a 1, 0x 1 0. So this would kind of be the address of this account. Would be like we go down at the 1 branch, and then we go down at the 0 branch, and we arrive at this account. But of course, like in reality, it's 32 bytes, and so the try is very big. If we would store all of the intermediate nodes, this would be incredible amount of storage. So what we came up with is this idea of the extension nodes. And we need basically this, like if you change something here, down here, if you say, okay, this is not 3 ETH anymore, but it's 4 ETH now, then this hash would change, and then this hash will change because it's a Merkle tree. So basically, this contains the hashes of all of the nodes. And so if this node changes, then this node changes. And if this node changes, this node changes. And this top node, the hash of this top node is in every block. So in every block, everyone computes these updates and then computes the state root and then verifies that this root is the same as in the block that they just received. And so the problem with this is, like, we could just store everything in this thing and it would be fine. The problem with it is, if we now want to read this, we would kind of need to read this node. Now, okay, the question is, like, someone sends money to account 0x10. What do? We need to know what is the current balance of account 0x10, and then we would need to update it. So we would need to go to this node and read it from disk and say, okay, I need all of your children, and I'm going to pick child 1, and then I will read this node. And then I will need to read all of the children and pick child 0, and then I will read this node. So that means that in order to read this account, we would need to do 1, 2, 3 lookups on the database. And in reality, we would need up to 32 lookups in the database. No, sorry, 64, because we are per nibble in the size of the account. Anyway. So we would need like 64 lookups in the database to find this account. And this is very, 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 very heavy. So what we do is we store all of the stuff like this. And in addition, we store the same data in a key value store where we say 0x10 to 4, where we just have like this address points to this node. And then we can like do like here, the lookup is O log base 16 of n. The lookup in this structure. The lookup in this structure is O of 1, because it's a direct thing. And so what we do is we store the same data, 150 gigabytes or 100 gigabytes roughly, twice, which is very wasteful, but we need it for 2 different things. We need it to compute the state root, and we need it for quick access in the EVM. We are.
I have a question.
Yes.
Yeah, probably I can go ahead. I've listened to how you've explained on the execution client layer with Geth. So my question is, for somebody who has some basic understanding on developing on application layer development, what would you advise them to focus on when they want to probably scale up to contributing to the core protocol on the execution clients?
That's a great question. I think something like testing is a great way to get into it, because you can focus on a very tiny part that you want to test, and from that you kind of scale up your knowledge about, okay, like usually you start testing within the EVM, which is like it's not a very complex, and it's not a very big kind of code base, and or like part of the code. And then you start with this and then kind of go to other things that are kind of interesting to you. Yeah, you can get the.
All right, thank you.
You're welcome.
So we are already 5 minutes late. So I think we can wrap up now. And yeah, thank you, Marius, for joining us and giving us a deep dive into the execution there. Thanks a lot. Bye, everyone.
Bye.
Yeah.
Thank you for having me. Bye bye.
Thank you. Bye bye.